Okay, continuing on physical chemistry, chapter 17, section 5. We're going to talk about rate laws and equilibrium constants for elementary reactions. Now remember, we said before, an elementary step is one that can't be broken down into smaller steps. Now let's define molecularity. That's the number of molecules, atoms, or ions involved in the elementary step. We're talking about the reactants only. For example, A going to one or more products. This is a unimolecular. This might be an example of a decomposition or isomerization. That would still count as a reaction. We could also have A plus A, or just 2A, going to one or more products. Then we would say this is bimolecular. Or we could have A plus B going to one or more products. Then we would also say that's bimolecular. Now we could also have A plus B plus C going to one or more products. We would say that's termolecular or trimolecular. Or we could have A plus 2B going to one or more products, and that also is termolecular or trimolecular. Or we could have 3A going to one or more products. That too is also termolecular or trimolecular. Now trimolecular is actually kind of rare. Now, if a proposed mechanism has a trimolecular step, it will raise skepticism because it's so rare. Now for an elementary reaction, let's say we have A amount of substance A plus B amount of substance B going to one or more products, then we could say the rate is equal to R is equal to a constant K times the concentration of substance A to this A power times the concentration of B to the B power. This is for an elementary step. An elementary reaction is the only time we can take the stoichiometric coefficients like that and make them the exponent in the rate law. Now, any bimolecular reaction is going to be second order, but not all second order reactions are bimolecular. So the question is, what is the relationship between K sub C, the equilibrium constant, and K sub F, the rate constant for the forward reaction, and K sub R, the rate constant for the reverse reaction, for an elementary reaction? Well, here's a similar reaction. We have A amount of substance A plus B amount of substance A, or B, those are our reactants. Then they're in equilibrium, so we have this forward rate constant, or this forward react constant, and this reverse constant, equilibrium constant, plus C going to C, and D to D. Those are the products. So this is for a reversible elementary reaction. So R sub F, so the rate forward is Kf times the initial concentration A times the initial concentration of B to the A and B powers respectively. That's for an elementary reaction. And likewise, the rate reverse is going to be Kr, the reverse rate constant, times the concentration C to the C times the initial concentration D to the lambda power. That's for an elementary, that's D. Can't read my own handwriting. That's elementary reaction. So remember, at equilibrium, the rate forward is equal to the rate reverse. So we have Kf is equal to initial concentration of A to the A power times the initial the concentration of B to the B power, and that's equal to Kr times the concentration of C to the C power times the concentration of D to the D power at equilibrium, because they're equal. So what we end up with is the K forward divided by the K reverse is going to be equal to the C to the C times D to the D divided by A to the A divided by B to the B. And that's going to be equal to Kc. So Kc, the equilibrium constant, is going to be equal to the forward rate constant divided by the reverse rate constant, but only for an elementary reaction. Now K sub C is thermodynamic. Now the C is actually because of the concentration scale equilibrium constant. Now remember, the forward rate constant and the reverse rate constant are kinetic. Now if the forward rate constant is much greater than the reverse rate constant, then Kc, the equilibrium constant, is much greater than 1, and equilibrium position will favor the product or products. If the reverse rate constant is much greater than the forward rate constant, then the equilibrium constant is much less than 1, and the equilibrium position favors the reactants. If Kc is much less than 1, the process isn't profitable. profitable if you're talking about an industrial process.